Hello! In this video, we are going to prove the following theorem. Suppose R is a relation from A to B. Then the domain of R is equal to the range of R inverse, and the domain of R inverse is equal to the range of R. Now, to prove this, we're going to start out by proving just this. So to begin our proof, let's give ourselves two sets A and B, and let's suppose that R is a relation from A to B. Right, and to say that R is a relation from A to B is another way of saying that R is a subset of A times B. Okay, now our goal is to prove that the domain of R is equal to the range of R inverse. Now, if you recall, since R is a relation from A to B, it follows that R inverse is a relation from B to A. And now, from the definition of domain, the domain of R is the set of all elements in this set, such that there is an element in this set where the ordered pair is an element of R. More precisely, the domain of R is the set of all elements X in A, such that there is an element Y in B, such that X, Y is an element of R. And from the definition of range, the range of R inverse is the set of all elements in this set, such that there is an element in this set whose ordered pair is an element of R inverse. More precisely, it's the set of all elements P in A, such that there is an element Q in B, such that Q, P is an element of R inverse. So now, we're trying to prove that these two sets are equal. And the way we can do that is we can show that everything in this set is also in this set, and everything in this set is also in this set. Let's start out by showing that everything in this set is also in this set. And to do that, give me an arbitrary element of the domain of R. I'll call it T. What does it mean for T to be an element of the domain of R? Well, if we take the X here and substitute it for T, what we have here is that T is an element of A, and there is some element Y in B, such that T, Y is an element of R. Now, if you recall, the inverse of R is really just the set of all ordered pairs in R where the coordinates are swapped. So really, T, Y is an element of R if and only if Y, T is an element of R inverse. So Y, T is an element of R inverse. But now notice, T satisfies all the requirements to be an element of the range of R inverse. Right? If we take P to be T and Q to be Y, well, yeah, T is an element of A, that's what we have right here, and we have that Y is an element of B, that's what we have right here, and Y, T is an element of R inverse, that's what we just found. So yeah, T satisfies all the requirements to be an element of the range of R inverse. So, putting this together, we started with an arbitrary element in the domain of R and showed that it also lies in the range of R inverse. Therefore, the domain of R is a subset of the range of R inverse. So now that we've shown everything in this set is also in this set, now we're going to show everything in this set is also in this set. And to do that, give me an arbitrary element of this set. Again, I'm going to call it T. What does it mean for T to be an element of the range of R inverse? Well, what it means is we can take the P here, replace it with T. So we have that T is an element of A, and there is some element Q in B, such that Q, T is an element of R inverse. But again, R inverse is just the set of all ordered pairs of R where the coordinates are swapped. So really from here, we have that T, Q is an element of R. So now, we can observe that T satisfies all the requirements to be an element of the domain of R. Right? Because if we take X to be T and Y to be Q, well, yeah, T is an element of A. That is what we have right here. And we know that Q is an element of B. That's what we have right here. And T, Q is an element of R. That's what we have right here. So yeah, T satisfies all the requirements to be an element of the domain of R. So, putting this together, we gave ourselves an arbitrary element of the range of R inverse and showed that it is also an element of the domain of R. Therefore, everything in the range of R inverse is also in the domain of R. So, putting this together, these two facts tell us that the two sets are equal. And that's exactly what we wanted to prove. So this completes the proof. So that proves what we first wanted to prove. Now we're going to prove the next thing we want to prove, which is that the domain of R inverse is equal to the range of R. And technically, it's going to be a corollary of what we just proved. Okay, so what do we just prove? Well, we just proved that given R is a relation from A to B, the domain of R is equal to the range of R inverse, right? And that is equivalent to saying, given J is a relation from C to D, the domain of J is equal to the range of J inverse. I hope you can see that it doesn't matter what I call these three sets, because in the previous statement that we proved, A and B were arbitrary sets. R was an arbitrary subset of A times B. So now, let's prove this corollary. And to prove it, well, let's suppose that A and B are two sets, and R is a subset of A times B. From here, we want to prove that the domain of R inverse is equal to the range of R. Now, based on what we have just proven, this statement is true. And it doesn't matter what C, D, and J are, so we can take C to be B, D to be A, and J to be the inverse of R. If we do that, well, we have that the domain of R inverse is equal to the range of R inverse inverse. But if you recall, given any relation R, R is equal to the inverse of R. So really, the range of R inverse inverse is equal to the range of R. So the domain of R inverse is equal to the range of R. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.